Welcome, everyone. Thank you for joining us for today's webinar. Today, we'll be discussing how to improve your PCB signal and power integrity with integrated layout analysis. My name is Supreet Manava. I am a product manager with Cadence in the PCB division, and I'm your host. Our presenter today is John Carney. He is a product engineering architect for OrCAD X, and today he's going to be covering how integrated signal and power integrity directly within the Cadence PCB environment can be used to enable faster, more accurate design convergence and reduce rework. So with that, I'll hand it off to John.
Hello, everybody. So what I kind of want to talk about today is the value of having an integrated analysis solution inside your PCB design tool. What we've done with this Aurora integrated analysis, we've taken expert level tools and integrated them right in the PCB design tool. So you may not be an SIPI expert, but you can set these analysis engine ups, run them, interpret the results, and then act upon the results all within your layout design tool. So you can find and fix signal and power integrity problems all within your OrCAD X layout tool or Allegro X layout tool. The value in doing that is immense, right? If you're not doing analysis of your design, you've experienced it once for sure, and if not, you're going to, where you build a design and it doesn't work. And then now you're looking at spending even more time and money because you're either having to debug the problem that didn't work and then rework it. So now instead of working on your next product or project, you've taken engineers and PCB designers offline to debug a problem. You've wasted money fabricating it. You got to get back in line with the fabrication queue. All bad news all across the board. So that's why you want to take the time to do signal and power integrity analysis on your design. And then having the tools integrated is immensely valuable because if you are using some third-party solver, that takes you out of your design layout tool. You're probably or maybe sending the design data to somebody else in your organization that may not understand the PCB. There's going to be some sort of translation of the design involved, so something may get changed in the translation. Then that person runs the analysis. And then if they find something that they think is a problem, how do they communicate that back to you? It's going to be screenshots, emails, and then you've got to figure out how to find that same location in your design, fix the problem, and then start that whole cycle all over again where you got to translate the design, send it to another person and wait. You know, I've seen situations where having an integrated analysis allows the designer to find and fix problems in under an hour, whereas the same workflow of using a third-party tool could take 3 to 4 days. So it's a massive time saver. And often these analysis tools are geared towards a signal integrity expert, not a PCB designer. So what we're showing you here is basically merging the best of both worlds. So here I am inside of a OrCAD X layout, and you'll find an electrical analysis menu in the new release, and that's going to open up this analysis workflow panel, giving you access to all of these different analysis workflows. Now, I should point out that with the OrCAD X professional license, you'll get the impedance and coupling workflow. That's included. The other analysis workflows do require a separate license, but it's still all completely integrated. And this is a integrated analysis tool that's completely integrated into the layout editor. So this is your full layout editor. You can do delay tuning, you can do component placement, you can add shapes, you can add via arrays. And the reason I point that out is because this is going to allow you to find a problem, and then you can fix the problem and then rerun the analysis. And you can do this at any stage in your layout design. You don't have to wait until the design is 100% placed and routed to do the analysis. If you're only interested, if you're working on this section of the layout right here, as soon as you've routed that section, you can analyze that one section. So you can cut up your design and analyze subsegments of it. So I'm going to walk through a couple of these different workflows to show you how they work. I'm going to first show you this design setup workflow. And this workflow is kind of giving the system the data that's needed for all of the other workflows in the design tool or in the analysis engine. A lot of this stuff is probably there already, but it's more of just a double check to make sure you have it. So for example, you're going to want to set up your cross section to make sure you have all the layers in your design that you want to analyze. You're going to want to make sure you have the correct materials in that cross section as well. And if you've noticed in the cross section editor, you can specify what kind of material this is, whether it's going to be copper, FR4. The tool comes with a large library of materials. If you're not using anything exotic, we're going to have what you're using out of the box. But some people use exotic materials, and you can modify those as well. If you want, you can define components as like inputs, outputs, drivers, receivers. You want to make sure you have your XNet set up. So an XNet would be a situation where you may have an address line or a data line that may have like a series terminator in it. And you want to analyze timing across from the driver to the receiver, not just from the driver to that resistor. And so going through this setup one time, that setup will be applied to all of these different workflows. Now, each workflow itself allows you to set those things up individually if you want to yourself. So first, let's look at impedance. Impedance doesn't require any models for drivers or receivers. It's just going to analyze the impedance of every routed trace in your design. And you can do this as a net-based or a directed group. I'll cover directed group when I get into the coupling analysis. And so the first thing you're going to want to do is select which nets you want to analyze. You can look at this from a flat perspective, which just gives you a list of all the nets in the design, or you can choose hierarchical that will then break it out based upon buses in differential pairs. That's normally a little preferable because if you have some high-speed interface, it's probably going to be in a bus. So you can pick which buses and diff pairs you want to analyze, or you could just analyze every net in the design if you wanted to. All these analysis engines use an integrated, we call it a 2.5D field solver. It's a patented field solver we have that will look at a PCB. And if you have a situation like this that has a long trace running over a solid reference ground plane, it's going to model that using a 2.5D solver. So it's accurate because there's no reason to go full 3D because it's not really a 3D problem. So that's speed. But once you get into an area like this where you have a lot of via transitions, a lot of holes, a lot of voids, that's a localized 3D problem where you do want to model it in 3D. So in those areas, it will use a 3D type of representation of the PCB. So you basically get a highly accurate yet highly fast field solver. Cadence does have complete full wave 3D field solvers if you need that level of analysis. Again, this is not like a sign-off level analysis. This is a find, fix, verify. Once all this looks good, then you might want to go into a full DDR system analysis or something like that if you're at that level. There are a few options that you can set up here. You can specify, how you want to handle special voids, what sort of field domain you want to deal with, how you want to model nets and shapes. Most of the time, the default settings here are going to be fine. If you're doing like, let's say, a 2-layer RF board that everything is just a coplanar, then you'd want to say detect and model coplanar traces. Then you have, oh, sorry, I already covered that. And then if you want to, you can choose this option to say crop area by selected nets. This design is not very big from the solver's perspective, so this whole design would take maybe under 2 to 3 minutes to run. But if you have a massive design, you can and if you told the solver that you were only solving these nets right here, setting that option is actually going to cookie cutter out that area of the PCB and only send that to the solver, making it run even faster, right? Because if you don't care about what's going on down here in the PCB, you'll get your answers even faster if you choose to crop by the selected nets. So once you run all that setup, this start analysis option will be enabled. I've already run the analysis prior to starting this webinar, so I'm just going to load the analysis results. So the analysis results for this analysis and all the analysis gives you the data in a couple of different ways. First and foremost, you're going to get this color-coded overlay showing you the measured value of the results. So it's showing you that you have a range of 17.5 ohms up to 17.8 ohms from a single-ended impedance value perspective. You can grab the bottom of that chart and kind of move it up. So if you really want to highlight, where the higher impedance values are in the tool, you can do that. So from that alone, you could just start looking around and zooming and say, oh, wow, those traces have an impedance discontinuity. Why would that be? Probably because there's a void in the reference plane layer under those traces. So immediately as a designer, like, oh, I got to reroute those traces or deal with the ground plane underneath it, because that impedance discontinuity could cause some sort of signal integrity issue. That's very valuable because right now you could go into the add trace mode, you can go into the add shape mode, whatever you need to do, you can go into visibility, turn on all your power planes to see what's going on. You can see there that, yep, there is a void in that plane layer right below it. So that's what I'm talking about, the ability to find and fix problems all in the design tool. You can switch this back from single-ended and you can go to differential. Now you are seeing your differential impedance values for all your diff pairs in your design. This can be highly valuable because if you expected a diff pair to have like an 80 ohm characteristic impedance, you've got some that have a lot more. Maybe you need to reroute it on a different layer. Maybe you need to do something else to change that. So this is the visual reference. And again, it doesn't mean that red's bad, blue is good. It just means that red is the highest value it found, blue is the lowest value it found. Another thing you can look at is table-based data. So this is modeling the impedance of every segment in the design. And so if you click on this table, you'll get the simulation table here, and you can dock it to the left, you can dock it down to the bottom, or if you had a separate monitor, you could dock it on a whole other screen. It's designed to be docked several different ways. I'm going to choose to dock it over here on the left because I kind of prefer to work it that way. So what this is telling you is it's giving you for every net in your design, how many V's you have, if it has a reference plane or not, minimum, maximum, and typical impedance, and then the length at that min-max typical impedance value, the delay, and the resistance, inductance, capacitance of that trace. You can look at that in terms of single-ended and also differential. So now you have, let me get this zoom thing out of the way, that up there. So you have single-ended diff pair values. And then for each one of these charts, if you really, let's say, wanted to zoom in on where is that maximum impedance. So you can click on any one of these column headers, sort by that column headers, and then it's telling you that this particular trace has a segment that has a very high impedance. If you select that trace, it now breaks that trace down here in the detail table to every segment of that trace, all the different lengths, the delay of the different lengths, what layer those different lengths are on. And so now you can look at this and you can say, well, where is this in the design? Double click on that, double click on anything for this trace table, and it's going to take you exactly to where that problem is at in the design. So now you've found a problem, and then now you can work on identifying ways to fix that problem in the design. So you could cycle through this, clean up any impedance value, reroute, add reference planes, change thicknesses, whatever you need to do. And then now, once the analysis is set up, you can just hit start analysis again. It'll rerun all these tables and graphs will update. You can see if there's any more extreme values, change the design, rerun the analysis, change the design, rerun the analysis. So it's this integrated solution that allows you to find problems, fix problems, becomes super valuable. Because if you could think of this workflow using some third-party analysis engine, you'd be looking at a picture right now in a document saying, hey, this looks high. What do you need to do about it? So you've had to find where is that in your design, right? Good luck doing that, and then resend it back. Next up, we're going to look at coupling. Coupling is similar to crosstalk, but it's a lot easier to set up than crosstalk. All coupling is going to do is measure how closely coupled all the routed traces in the design are. And if they are closely coupled, then that would mean that if they are active at the same time, you could have a crosstalk problem. But it doesn't require you to set up IBIS models of drivers and receivers because it's not actually sending any signal down the routed traces. So For a crosstalk model, again, you have to select the nets that you want to analyze. And in this case, I'll choose a directed group, and I'll show you what a directed group is. A directed group is basically a driver-receiver pair. So here I've said I want to analyze the nets from this BGA to these two DEM connectors. You could also say I want to analyze the nets from that BGA to that jumper. This gives you additional data at the end. So instead of just getting coupling values, you'll get coupling values starting from a certain location, ending at another location. So that's the value of setting up these directed groups. Again, you have the same ERC options that I showed you before that you can walk through and set up if you need to. And then same as all the other ones, you can crop the area by the selected nets to, again, speed up the simulation time. So once you've set that up, you could start the analysis. I'm going to load the analysis results. And for some reason, my mouse decided to malfunction. Okay, got it back. So, so what this is showing you now, using the same type of visual overlay that you had before, is a coupling coefficient, how tightly these routed segments are coupled. And this is doing it not just on the same layer, but on multiple layers. So you can see in here where you have all these routed signals going through the BGA via field, you have a lot of traces on top of each other that are highly coupled. If those are all going to be active at the same time, or one's an aggressor, one's a victim, you're probably going to have a crosstalk problem. So same as before, as a designer, you can use this to, highlight the problem nets in the design, go in here and consider some reroute strategies to mitigate those problems. Same as before, you can look at this in terms of a worst case mode or a victim mode. So that's going to show you the victim perspective. And you can also look at it from a directed group perspective. And once you choose directed group, if you then choose to look at the coupling tables, over here now you have, oh, my mouse keeps crashing. Over here, it's going to show you all the different nets in the design. And then now you can see the aggressor or the coupling value for each net in the design. And again, you can walk through all these things to find that particular problem in the design. If you look at the coupling tables, or I'm sorry, the coupling plots, let me bring this up a little bit. So this coupling plot is going to show you, this is what you get when you choose to set up the directed groups. This is going to show you for every net in the design. So the length across here is representing the routed length of the design. So this is a relatively short net. This is a relatively long net. And then the colors show you where in that net you have something that's highly coupled. So this is where this lets you kind of visually see where you have high coupling events in the design, medium coupling events, low coupling events in the design. And these things, again, allow you to select it from there, go to that part in the canvas to find where those problems are at. I'm going to switch to a different design now, and I'm going to show you the IR drop workflow. IR drop workflow is more power-based instead of signal-based. And this can be very important. Even if you have a design that doesn't have high-speed interfaces, it may be a low-power design. So you want to make sure all the devices have the correct power supply going to them. Otherwise, you're going to have a malfunction. So for this type of design, for this type of setup, you do need to identify the VRMs in the sinks. Where is the power coming into the design? What devices are syncing current from that power? And how much are those devices syncing? You can take a couple of approaches to set this up. You can choose to set up VRMs and sinks, and this is kind of like the most basic setup. This is a table that just gives you a list of all the power supplies in the design, and then you can specify for each power supply which component is syncing that, or which component is the VRM in the design for that power rail. And then you can go through and you can set up the sync currents as well. You can also use a capability we have called Power Tree that's a more advanced and more explicit setup. and that's integrated in our Allegro X system capture platform and also as a standalone tool. That allows you to get very specific down to a pin-to-pin level as to how much current each individual pin is selecting. So once you set up those analysis options, you can also cut by selected nets. And since sometimes these problems can get kind of large from a computational perspective, this is the first case where you have the option to enable distributed computing. So you could even distribute this problem. If you have like a server farm at your Access or cloud computing, you can submit this up to a couple of systems and then get your answer even faster. And so from this perspective, I'm going to now show you what these analysis drop results look like. So this is going to give you a couple of different displays. So you can look at it across different layers in the design. I'm looking at the power layer 17. This is where the main power rail is being distributed for this power rail. And you can look at it in terms of IR drop, voltage, current density, or current. So let's start with voltage. This here is telling you that, you know, this whole particular area here is only getting about 1.02 volts. If that was supposed to be getting 1.5 volts, you have found a problem that you definitely need to fix. If you were to look at something like current or current density, you can show the current vectors so you can see which way the current is flowing in the design and how the current's flowing around different via fields, etc. So it gives you a lot of good visuals to allow you to see what's going on with the power in your design. And like every other aspect, from here, you could go into the shape utilities and start making these shapes bigger. You could add more copper planes. You could add more vias. You could start moving parts around, but typically the result's going to be to add more copper or more conductor in here somewhere in the design. Same as the other analysis tools, you also get different tables that you can look at in the design. So you can see for every power net in the design, you can see output currents for every pin in the design, and you can see the sync voltage for every pin in the design. So you can see for every device and every pin, if you have a pass-fail status. So if you have pins that are supposed to be getting a certain amount of power or a certain amount of current, and they are not, it's going to tell you that you have a failure at that particular location of the design, and then you can go to that location in the design. This is very useful because if this is not a situation where a 98% is considered close enough to passing. If you have one pin on a IC that's not getting enough power, it's probably going to malfunction, and then your whole design is garbage. So having this pin level detail is very valuable. Okay, back to the other design. So now I'm going to switch to the reflection workflow. This one is a little more advanced in terms of the design setup, where you would need to set up models for the drivers in the receivers. So if you need to, this is where you could set up your components and assign a specific IBIS model for a driver in a receiver. If you don't have those, there's whole other sets of material we have on how to find and assign IBIS models. They typically come from the component vendor. So if you have a memory component, you're going to get the IBIS model from the memory vendor. If you have a processor, you're going to get the IBIS model from whoever sold you the processor. So once you get those IBIS models assigned, same as everything else, you select the nets, determine the nets you want to analyze, and run the analysis. So I'm going to load the analysis results and show you the type of results you get from this. So here you get a large family of analysis results. So let me bring up the reflection tables. So you can look at this. So effectively what this simulation is going to do is it's going to take the device that you've identified as a driver using the IBIS model and start sending pulses down all the lines from the IBIS model and then measure the effects at the receiver. That's what the reflection is going to do. So it's going to measure the effects at the receiver and even back at the driver. And you can measure those things from a couple different perspectives. You can look at ring back margin high and low. jetic overshoot high and low, propagation delay, first switch rise and fall, final settle rise and fall. So let's look at first propagation delay. Propagation delay, it's going to color your nets based upon their propagation delay value. And then again, for each net in the design, if it has multiple segments that have different propagation delay values, you can use this table to find those different nets that have those different delay values, and then double click on that and then zoom to that area in the design. The solution for this is probably going to be some sort of delay tuning, phase tuning, or rerouting the net to make it shorter or longer, whatever you need to do. If you're to look at like jetic overshoot high and low, it's letting you know which nets have an overshoot high problem or an overshoot low problem. Bring back high and low. Hopefully you're getting the idea now. Every one of these different measurements gives you a list of the results in this table here, and you can then use that list of results to navigate to that particular part or that particular net in the design, or you can just use the graphical overlay to visually see which one of these segments has a problem. So these types, this is kind of like a first order analysis to an ultimate sign-off analysis, right? If you had a DDR memory interface, you're going to eventually run a full system analysis, analyzing every bit of the bus at the time, getting it down to eye diagrams and some sort of verification utility. But if you do this first and flush out all these problems, the chances of that final analysis being successful are much higher. And if you were to run that final analysis and you failed there, this would be the way that you would debug that failure. You would try to find out like, oh, is my eye closed because I have a propagation delay problem? Do I have an overshoot problem? Do I have an undershoot problem? These things are all going to contribute to that final sign-off. Lastly, we're going to look at crosstalk. Same as every other analysis, you can select the nets in your design, set up the analysis options, cut the design by the area, and enable distributed computing. And let me load the analysis result. Oh, it's already loaded, so I don't even have to load it. So this is showing you, again, the color-coded results here, showing you the millivolts of crosstalk on every net in the design. And you can look at the tables to see for any net in the design which net has the victim receiver. So you can look at it from the perspective of all neighbors. So this net getting affected by every neighbor at a time, or from an each neighbor perspective. So you can see the effect of each individual net on each victim. Same as before, you can dial in from here and click on to find that particular net in the design. And you can even select these charts here to see the measured crosstalk from the victim and the aggressor, if you want to go into this level of detail. Same as all the other simulations in the design. If you realize this was a crosstalk problem, you could go into the add connect modes or the delay tune modes or the slide modes and start sliding and pushing these nets around. Sliding these pushing nets around, rerun the analysis, find and fix problems. So as a PCB designer, you're now really empowered to look at these problems, set up the analysis, run the analysis, and fix it, all while you're in your layout tool. Never left your layout environment, same use model as everything else in the layout tool. So having it completely integrated, now you can become the signal and power integrity expert in your organization and add more value to yourself, get your designs fabricated the first time so they're going to work. So that concludes the demo. I ended quite quickly. It didn't take the full hour, but that was everything I planned on showing today. I guess we can open it up to Q&A now.
Sure thing. Thanks, John.
Mm-hmm.
We had a few questions about the packaging of the analysis tools. So maybe we can start by talking about what you need to access the analysis workflows that you showed.
Sure. So with the OrCAD X professional license, you'll get access to the impedance and coupling workflows. All these other workflows are sold in a package we call Aurora InDesign Analysis. And so you buy that one license, and then you can You can run all of these different on license.
Yeah.
So what we often see, you know, at an organization is they may have, let's say, 5 designers. They'll get 1 Aurora license because they don't all need to be analyzing at the same time.
Right. There's also a model that uses tokens. If you're not aware of that, you know, you can reach out to us or reach out to your account teams, and they can let you know about these Sigrity tokens, which will allow you to have access to some of these tools as well. Also, you mentioned this for OrCAD. Is there any difference if we have Allegro users?
No, it's the exact same. It's the exact same engines and that exact same user interface. So we do that a lot in our R&D. We will develop a solution once and apply it to both of our platforms. So this analysis workflow has actually been available in Allegro for probably 8+ years. We keep adding. We'll add new analysis workflows, like we just added thermal 2 years ago. But this is also available in the Allegro platform.
All right. I have a question here about some of the stuff you showed. All right, is the coupling coefficient check applied to traces on the same layer, or is it applied to traces on adjacent layers?
It's adjacent layers. Yeah, it'll do both.
Right. Then, can you give a quick demo on the topology extraction and simulation?
No, not set up to do that right now.
Okay.
We do have YouTube videos that cover it. I could try, but it may not work out right. But
All right. Yeah. So topology extraction, what we can follow up on that. All right. It says it looks like you are in a viewer mode. Is it possible to do this in an Allegro viewer?
this is not the viewer. This is the full-blown layout editor. So for example, this is our new Allegro X and OrCAD X UI. It does look like the viewer. The new Allegro X viewer looks a lot like this. But this is a full-blown editor.
All right. For the coupling analysis, do you always assume that there is a ground plane underneath of the traces, regardless of the design, or do you consider the real plane design that is within the design?
It considers the real design. It doesn't assume any planes. So if there's not a plane, it'll model it as not having a plane. So you definitely want to make sure you have your make sure you have your grounds in there.
Okay. All right. I think here's a question on accuracy. So what you showed today, what information do we have on, the accuracy of the solvers?
They've been battle tested and correlated and benchmarked. These solvers have been at Cadence for over 15 years, I believe. And so they've been correlated with normally lab measurements verified by manufacturing. And then we ourselves have, since we have our own full wave 3D solver, we often do our own correlation of these fast solver results with the 3D solver results to ensure they're accurate. And we've also been in several competitive situations benchmarked against other field solvers, and we're almost always just as accurate and a lot faster.
All right. If an impedance controlled trace has a target impedance of 100, but impedance of this trace is 90 ohms on the inner layer, is it acceptable? Will it cause reflections? Yeah, I guess that's more of a question that you can model that with this if you have the traces set up with those impedances on these different layers, but I think that's more of a question of your judgment, right?
Yeah, exactly. It's like it may or may not, depending on the signal that's going down there. So in addition to these analysis inside of our constraint manager, you can set up impedance constraints. So you could specify, I want this net to have a target impedance, you can specify a tolerance on it. And then if it'll actually give you a DRC error to let you know that you are outside that range. And then it's up to you as a designer to understand, if this was supposed to be 100 ohms and I've got a segment that's 90 ohms, is that or is that not going to cause a problem with the signal integrity of the signal going down that trace, right? And I would look at it like, if you can fix it, you may well fix it. Only in the situation that there's absolutely no way to fix that impedance discontinuity would you then have to go into looking at the other analysis results, like, so let's say you first did impedance and you saw an impedance discontinuity. You could then look at the reflection to see, look at the reflection analysis on that net to find out, well, is that impedance discontinuity causing a large amount of reflection based upon the driver that I'm pumping down that? And then if that is causing a large amount of reflection, then you probably have a serious problem that you got to rework the design. If the reflection results looks okay, maybe it's low speed, maybe it's not a super critical signal, maybe there's good error correction on the device, maybe you're going to be okay.
Yeah. Thanks, John.
Mm-hmm.
Since you are on the impedance workflow there's a request to review how you started and set up the simulation after you selected a net for impedance.
So after you select the nets, right? So whatever, let's say I'm just going to say I want to do all the nets. Then this start analysis would turn blue and you just hit the start analysis and the analysis would run.
All right.
So this start analysis will be grayed out until it knows it has all the setup ready to run analysis. And so for impedance, the only thing it absolutely requires is for you to tell it at least one net to analyze. And once it has at least one or more nets, it's good to go and it can run the analysis. Same thing for coupling. The only real requirement for coupling is tell me what nets to analyze.
Yeah. And I think broadly speaking, these workflows, you'll see that they follow this top-down workflow within the UI. So there should be a nice workflow built into this that directs you on what your next step should be to be able to get the analysis running.
Exactly.
Okay. All right, I think this goes back to our first question. Are these workflows only available in the Presto editor, or can they be used in the PCB editor tool as well?
Yep, they're all available inside the Allegro PCB editor. Matter of fact, I'll fire it up to show you.
Okay, we had some questions on how to generate the power tree while you're doing that. To talk about that a little bit, you can generate them from Sigrity power tree if you have that installed and available. Otherwise, you can, if you're using a tool like System Capture, you can generate a power tree in there, and then that will output the power tree setup file, which you can reference within that IR drop workflow.
Yep, exactly. Yeah, so here I am in the Allegro PCB editor, and here are the exact same analysis workflows.
Yeah, perfect. I think there was a question about eye diagrams. I don't know if anything that you showed today required an eye diagram setup.
No, that's normally a sign-off level type of analysis. So all these analysis are, you can kind of think of it as single net analysis. It's analyzing this signal, then this net, and reporting on each net individually. An eye diagram is typically a composite of one or more nets overlaid on top of each other, normally used in like a compliance kind of report sign-off. And so we absolutely have capabilities to do that with our System SI solution, where you can then extract the whole router topology and analyze it at an eye diagram and throw it at a compliance kit, but that wasn't covered today.
Okay. All right, we have some feedback on the way that the results are reported. So the scales that are shown, say you have a very high impedance or you have something that is slightly over the threshold of the scale, that makes it hard to differentiate. Is there any adjustability in terms of the scale, maybe with the example of an impedance?
So I think what they're trying to say is they want more fidelity, let's say between 100 and 112. So they kind of want to say like, all right, I want to peg my display to this. And then now I want to color this range from like a blue to red. So I can really greatly better see, what is 101 versus 105. I
Yeah,
think that's
exactly.
what right now, no, there's from this visual perspective, there's not, but I would direct them to just over here, right? Where here you can explicitly see every individual value. And here you can see, I've got a 66.8 and a 75.7 and a 52. And even though visually their colors may exactly be the same, but here you can explicitly see the exact number you want and then just go into that, right? And then
Yeah.
dial in from down here. So it's kind of like at that level of fidelity, we just give you the exact numbers instead of a color. But point taken, there could be a cool option to change that.
Yeah. And I think you would have noticed John was able to dim the editor by adjusting that scale. So if you want to just really focus on a certain set of results visually, then you can go look at the table like he did. Right. What is the difference between the crosstalk and coupling analysis?
So crosstalk coupling does not actually send any signals down the line to measure victims or aggressors. So it doesn't actually measure crosstalk. All coupling is looking at is the fact that these traces are routed parallel to each other. And this is back to the other person's question. So these right here are even on tangent layers above and below each other. So it knows that because they are parallel to each other for a certain distance, they are highly coupled. And so this is telling you what percentage those are coupled together. Because they're highly coupled, if you do pump a signal down them at the same time, you're probably going to have crosstalk. So it's kind of telling you that you have a crosstalk problem without actually running crosstalk analysis, because the biggest contributor to crosstalk is coupling. So it's kind of like measuring the coupling effect without actually having to run crosstalk. Whereas with the crosstalk, you actually have to assign, an IBIS model to the driver receiver, and then it uses that IBIS model to pump a signal down every single net or multiple nets at the same time, and then measure the effect of crosstalk on each other net that's quiet. So for the crosstalk analysis, it may like hold this net quiet and pump signal down all of its neighbors, and then measure the measured crosstalk.
Perfect. Yep. So they go together, but yeah, slight variance in how they report results. On the coupling calculations, this person's asking, do you consider the E field or H field?
The E field, yes. The H field, I'm not sure.
Okay, you can follow up on that.
I'm pretty sure it does.
Oh yeah, it does both. We had somebody chime in. Thank you. All right. Okay, I think this is one that I haven't asked yet. Does the impedance workflow consider traces with solder mask openings?
Yes.
Right. Excellent. I think that's all the questions that have been asked so far. So thank you all for attending and for your questions. If you'd like to join us next month, we're going to have another webinar on September 10th that will be covering PSpice analysis. So if that sounds like it's of interest to you, please keep an eye out. And yeah, we look forward to seeing you then. Thank you.